Hello and welcome to a screencast on the average rate of change of a function. Given a function that models a certain phenomenon, it's natural to ask questions like, how is the function changing on a given interval? Or, on which interval is the function changing most rapidly? The concept of average rate of change enables us to make these questions more mathematically precise. So let's look at a specific example. The function a equals f of t models the temperature in Allendale, Michigan, t hours after midnight on an early September day. We see that the input is t, time in hours, after midnight, and the output is temperature A in Fahrenheit. We also see that at 1 a.m. the temperature was 56.4 degrees Fahrenheit, and at 2 p.m. the temperature was 74 degrees Fahrenheit. What can we say about the temperature on the interval from 1 to 14? So this interval is inputs. In other words, what can we say about the temperature between 1 a.m. and 2 p.m.? Pause the video and take some time to make some observations yourself. While many observations can accurately be made about this situation, I want to draw your attention to 5 key observations that will help us better understand the meaning of the average rate of change. So first, notice that our function a is positive on the interval from 1 to 14. That is, the graph is above the t-axis. So contextually, this means that the temperature is positive between 1 a.m. and 2 p.m. We also see that the function a equals f of t changes from decreasing to increasing on the interval 1 to 14. So in other words, the temperature was decreasing from about 1 a.m. to about 5 p.m. and then the temperature began to increase between about 5 a.m. and 2 p.m. Notice that saying a equals f of t is positive is different than saying that a equals f of t is increasing or decreasing. Some students mix up those words, positive and increasing versus negative and decreasing. They mean very different things, so be careful. Third, we see that the output in this function changed by 17.6 degrees Fahrenheit. Right? If we take the final temperature, 74 degrees Fahrenheit, and subtract the initial temperature on the interval, 56.4 degrees Fahrenheit, we get that 17.6 degrees. So that means that the temperature increased by 17.6 degrees Fahrenheit between 1 a.m. and 2 p.m. The fourth thing we can say is more about the interval. We can say that this interval from 1 to 14 represents a 13-hour interval. And so that's going to help us with this last observation. So we can ask ourselves, on average, how much was the temperature increasing every hour between 1 a.m. and 2 p.m.? And to answer this, we can take the change in temperature, 17.6 degrees Fahrenheit, and divide it by the number of hours that have passed, 13 hours. And this gives us approximately 1.3 degrees Fahrenheit per hour. So we can say that on average, the temperature increased approximately 1.3 degrees Fahrenheit per hour on the interval from 1 to 14. In other words, on average, the graph of a equals f of t rises vertically 1.3 degrees Fahrenheit per every increase of 1 hour. Let's explore the average rate of change in this context a little more. So first, how is the average rate of change computed? What did we do? Well, on the previous slide, we calculated the average rate of change by taking the change in temperature and dividing it by the change in time. More generally, we divided the change in output by the change in input. Second question we could answer, what is the significance of the units on the average rate of change? Well, because the average rate of change is change in output divided by change in input, the units on the average rate of change were the output units per one input unit. It's important to note that we actually did that division, so the average rate of change is always describing the change in output units per one unit of input. Third, what does the average rate of change represent graphically? Well, on the previous slide, we noted that the temperature rises by 17.6 degrees Fahrenheit between 1 a.m. and 2 p.m. And if we draw a line between the two corresponding points on the graph, you might recognize that 17.6 represents the rise, and the 13, which was the length of the interval, represents the run. So the average rate of change, 1.3, actually represents the slope of this line that connects the two corresponding points on the graph of A equals f of t. It's important to notice that while this line is increasing by 1.3 degrees Fahrenheit per hour, the actual curve, A equals f of t, is increasing at different rates. But on average, this curve is increasing by 1.3 degrees Fahrenheit per hour. Lastly, what's the significance of a positive average rate of change? Well, the positive average rate of change tells us that on average, the temperature is increasing between 1 a.m. and 2 p.m. But again, it's important to notice the temperature is not always increasing on this interval. That's why it's important that we include this qualifier on average. All right, let's summarize what we've seen in this context and try to describe how to find the average rate of change in general. So for our function g, defined on the interval a to b, note a and b are input values. Both of them are input values. Then the average rate of change of g on the interval from a to b will be denoted by this notation, a of v sub the interval a comma b, and it's calculated by g of b minus g of a, which is the change in output, divided by b minus a, which is the change in input. Graphically, if this is the point a comma g of a, then we can label the axes. So we have input a, and we have output g of a. And if this is the point b g of b, then the input is b and the output is g of b. And the average rate of change is g of b minus g of a, which is this vertical change between the points, divided by b minus a, which is this horizontal change between the points. So furthermore, in our example, we saw that the value of the average rate of change on the interval from a to b is the slope of the line that passes through the points a g of a and b g of b on the graph of g. We also saw that the average rate of change tells us how much the function rises or falls on average for each additional unit that we move to the right on the graph. So if the average rate of change is positive, then the function g is rising on average. And if the average rate of change is negative, then the function g is falling on average. And lastly, we noted that the units of the average rate of change on the interval from a to b are the units of the output per one unit of the input. In future videos, we'll practice computing the average rate of change in functions defined by tables and formulas, and we'll look again at what the average rate of change tells us about a function.